All right, welcome everybody. Today we are going to talk about lesson number 22, and this is your first day of section 2.6, which is an introduction to something called related rates. Before we get started, there's a couple of things I want to point out. So first of all, please make sure you're aware that this front and this back, these are both the lesson 22 and homework 22. So as long as you fill in the notes while we go through the lesson, you won't have a specific homework on this section. This is really just an introduction to kind of set the scene for the lessons that follow. Something else, related rates is one of the most important topics in calculus because it really is the first time that you're seeing an application of the derivative. So that's going to happen, of course, in the form of a word problem. So we're going to be talking about related rates for several lessons here. So taking a look at number one, we're going to go ahead and use implicit differentiation to find dy dx if given the following. So of course, when you're using implicit differentiation, that was section 2.5, you have to be told what variable to take the derivative in terms of. And so we mostly have been doing dy dx. We are going to change that up a bit in just a minute, but we're going to go ahead and keep that for the first one. Secondly, just kind of notice here that this is the same worksheet that you have. I just went ahead and kind of made the font a little bigger for those who were in the audience, so it was a little bit easier to see. So as we go to do the implicit differentiation to find dy dx, remember that generally speaking, if your value is an x, you're going to take the derivative like normal. If your value has a y, you're going to take the derivative like normal and then follow it up with a dy dx. So as I go to take the derivative of the cosine of x, that is the negative sine of x, plus x squared times y, that's the product rule where x squared is the first and y is the second. So the product rule says you're going to take the first, which is x squared, times the derivative of the second. So the derivative of y would be 1 dy dx, plus the second, which is y, times the derivative of the first, which would be 2x, plus the derivative of 4y cubed is bring down the 3, 12y squared, and then follow it up with a dy dx. And of course, the derivative of a constant is always 0. From here, I'm going to gather up all my dy dx terms and put them on the left. And then I'm going to go ahead and move everything else to the right. So that's going to give me x squared dy dx plus 12y squared dy dx. And then if I go ahead and move everything else to the other side, that's going to turn into a positive sine x and a negative 2xy. So from here, I'm now going to factor out my dy dx, which is going to leave me with x squared plus 12y squared. And then in my final step, to get the dy dx, I'm going to go ahead and divide. So my final answer here is going to be the sine of x minus 2xy divided by x squared plus 12y squared. There is nothing that is common to all four of those values. So there's nothing I can factor. There's nothing I can simplify. And that's really as far as I can go. So that was really just a refresher, really nothing new about that problem as opposed to the ones we did in section 2.5. But it is kind of good to just kind of get us started with something that's familiar. And now let's go ahead and see how we're going to apply this in a slightly new way. So notice here for number 2, you're going to suppose that x and y are functions of t. So we've seen time in several of our word problems, but we never really have done it in terms of a derivative. So that is a little bit new. So in part A, notice that you're given the equation x squared plus y squared equals 4, and you're asked to differentiate with respect to t. So if you're being asked to differentiate with respect to t, what you're being asked to find is d dt. So what that means is that if there were any t's that were in your equation, you would take the derivative like normal. If you have any variable that is not a t, you have to take the derivative, then follow it up with a d dt in terms of whatever the variable is. So let's go ahead and try that. So here in A, the derivative of x squared, take it like normal, 2x, and then you have to take the derivative in terms of t, which means you're going to follow it up with a dx dt. Plus the derivative of y squared, you're going to take it like normal, 2y, and then you're going to follow it up with a dy dt, and then the constant, of course, has the derivative of 0. So anytime you're asked to differentiate with respect to t, you typically won't have a t in the problem, which means that every other variable, you take the derivative like normal and follow it up with a d, whatever dt. So then in part B, it says dx dt is -2, find dy dt if I give you x and if I give you y. So basically, you're taking the answer that you had in A, and now you're actually solving for something. So that, again, is a little bit new. So let's go ahead and plug in the values here. So we're going to start off with 2, x is 1, dx dt is -2, plus 2, y is the square root of 3, dy dt is what I'm trying to solve for, and that is equal to 0. And remember, remembering that the derivative of a constant is 0, that for some reason is always a common mistake. If you were to leave that as a 4 as opposed to a 0, it makes the problem much, much, much harder. So just make sure that you're cautious when you're doing that. So as I go ahead and simplify here, 2 times 1 times -2, that of course is -4, plus 2 radical 3 dy dt is equal to 0. I'm going to add the 4 to the other side. So 2 radical 3 dy dt is equal to +4. To get dy dt by itself, I, of course, am going to divide by 2 radical 3. So 4 divided by 2 radical 3, 4 divided by 2 is 2 over radical 3. Multiply top and bottom by radical 3 over radical 3. You're going to get 2 radical 3 over 3, and that is going to actually be equal to dy dt, and that's exactly what we're looking for. So in most of these problems, your final answer is no longer going to be an equation, but it's actually going to be a quantity. So from this point forward, or at least once we get really into related rates, you are going to actually be solving for some numerical value. So let's go ahead and see something that's a little bit in the similar vein. So take a look at number 3. If xy is equal to 12 and dx dt is equal to 3, find dy dt when y is 2. So just by looking at this problem, the fact that the original is only xy and the fact that you're being asked to find things with dt's is kind of how you know that you have to differentiate with respect to t. So just something that you want to be on the lookout for. So as we go to take the derivative of xy, again, you'll notice that that is a product where x is the first and y is the second. So in order to take that derivative, it's the first, which is x, the derivative of y, which would be 1, and then follow it up with dy dt, plus the second, which is y, times the derivative of x. So the derivative of x, again, would be 1, but then dx dt. And of course, the derivative of 12 is 0. So from here, you would be looking to now plug in for all the values that you know. And as you go to plug in, you realize that you don't have x. So did I give you a problem that doesn't work? Never. You have to have enough information to solve it, which means even if the information is not explicitly stated, you do have to be able to calculate it. So if you want to solve for x, if you go back to the fact that xy is equal to 12, and you know that y is equal to 2, then if you plug a 2 in for y, you should be able to very easily tell me that at this point in time, x is equal to 6. So just kind of something to wrap your mind around as we progress through these problems. We always know that there's enough information given to you. So even if it is not explicitly stated, you just might have to take a couple of seconds to go back and find it. So in this particular case, we're going to put a 6 in for x. Dy dt is what we're looking for. Plus 2 dx dt is 3 equal to 0. I'm going to go ahead and subtract the 6 to the other side. So 6 dy dt would equal -6. Divide by +6, and you get that dy dt equals -1. The whole point about the related rate problems that we're going to get into is that dy dt is actually going to mean something. It's actually going to mean something very important, but we'll get to that in a couple of minutes. So now let's kind of bring in some of the most basic word problems just to see, again, as we get a little bit harder as we go here. So Sheila walks to Lake Monoman and throws a rock into the water. Since the lake is calm, ripples in the shape of concentric circles are formed on the water. So hopefully at some point in your life, you have seen somebody throw something into a lake and you see how circles appear, and they're kind of smaller right around the object that you threw, and then they get larger as they spread out. So that's what they mean by concentric circles. So they want you to assign variables to the area and radius of one of these circles. So not meant to be a trick. If you're trying to find the area, you would most likely give that a variable of a. If you were talking about the area of a circle, you of course would be talking about the radius. So the radius of a circle, you would typically use r. So again, math people are not that clever. Use the most obvious variable in all situations. So now that you assign some variables, you're going to go ahead and set up an equation relating the variables. If we're talking about the area of a circle, hopefully area equals pi r squared should be the equation that comes to mind. And then differentiate with respect to t. So again, you're going to take the derivative of a equals pi r squared. Be mindful of anything that's a constant. Anything that is a variable, you're going to take the derivative and then follow it up with a d, whatever the variable is, dt. So as we go to take the derivative of a for area, this is technically a to the first, which is really the same as x to the first. So the derivative of something to the first would just be 1, and then dA dt. Remember, take the derivative of that variable in terms of t. How would you take the derivative of pi r squared? Well, pi is a constant. So bring down the 2 times pi. R would go to the 1 less power, and you would follow it up with a dr dt. So again, eventually there'll be more work to be done. You'll be solving for things. You'll be explaining things. But for now, we just want to get used to assigning some variables, remembering all those important geometrical equations, and then taking the derivative pretty much always with respect to t. All right, so here in number 5, car A is going west at 50 miles per hour, and car B is going north at 60 miles per hour. Both are headed for the intersection of the two roads. Set up an equation relating x, y, and s, and then differentiate with respect to t. So for a lot of these related rate problems that are going to occur, you're going to be asked to draw a picture, but notice that I kind of drew one for you. So you have car A, which is heading to the west. Then you have car B, which is heading to the north, and they're both headed for this intersection over here. So notice that I gave you some variables. I told you that this horizontal distance was x, this vertical distance was y, and then I made the third side s. We're going to differentiate with respect to t, so that's something to keep in mind. And then as we go to set up an equation, something I want to point out here. So you know how fast car A is traveling, and you know how fast car B is traveling. So what those values represent are talking about a change. If ever you're talking about a change, that means that you are only allowed to plug those into a derivative. You're never allowed to plug those in to the first step. So that 50 and that 60, you would need it eventually if we solved the problem all the way through. But because those are values of change, you're only allowed to plug them into the derivative. So that's true now, and that's true always. So we're trying to set up an equation that relates x, y, and s. So hopefully you notice that this is a triangle. Not only is it a triangle, but it's a right triangle. So the most obvious way to connect the three sides of a right triangle is, of course, the Pythagorean theorem. So we're going to say that x squared plus y squared is equal to s squared. And again, those variables were given to you. If you were going to assign them on your own, they would be slightly different. Then we're going to differentiate with respect to t. So take each of the derivative and follow it up with a derivative with respect to t. So the derivative of x squared would be 2x followed by dx dt plus 2y followed by dy dt plus, equals 2s followed by ds dt. And again, this is just the first of many steps in these related rate problems. You would then have more to do, but for now, we're just trying to kind of focus on the basics. So one more in terms of being able to set up, and just so you know, not only are these kind of just meant to set the scene a little bit for related rates, but these are the most common types of problems that you're going to see throughout the next couple of lessons. But again, this is just the first step of 6 or 7 steps. So there's still a lot more to come. So a person who is 6 feet tall walks away from a streetlight that is 18 feet above ground level. So if you kind of notice what's happening here is my 6 foot tall person. He is walking away from a streetlight that is located 18 feet above the ground, and he is walking away at a rate of 5 feet per second. Something that I want to just again point out here. So that rate of 5 feet per second, that is a value of change. If you're talking about a value of change, that is allowed to go into the derivative only, which means it would never be part of your original equation. So set up an equation relating x and y and then differentiate with respect to t. So after this guy walks away from the street light, he has walked some distance, which we're going to call x, and then he stops, and then it is some distance y to the tip of where his shadow would be. So it doesn't really get into it, but this problem would really be about shadows. So from here, you're going to set up an equation using x and y. Maybe it kind of came to you, maybe not. Yes, it's a right triangle, so you might think to yourself Pythagorean theorem, but because of the fact that we don't know anything about the hypotenuse, not only do we have one triangle here, but we actually have two right triangles, which means that the technique we're actually going to use is the idea of similar triangles. So more so than ever for this topic, you kind of have to reach back to your geometry days. When it comes to similar triangles, remember you're trying to compare the small right triangle here to the large right triangle. There are lots of different ways that you can do that. I'm just going to show you one. So let's go ahead and look at that small right triangle. I'm going to compare the vertical side 6 to the horizontal side y. Whatever comparison I do on the small triangle, I now have to do the same proportion for the large triangle. So I did the vertical side of the small, which means I now have to do the vertical side of the large. Then I did the horizontal distance of the small, so I have to do the horizontal distance of the large. And the horizontal distance of the large is that entire quantity x plus y. So here I have my equation, and I do have to differentiate with respect to t, but taking a look at this, this is not actually a friendly way for me to take the derivative with respect to t. I could, but I'd have to use the quotient rule twice. Yeah, I strongly recommend not doing that. What I would recommend doing is cross multiplying. So if you cross multiply, you're going to get 6 times x plus y equals 18y. Then, still don't take the derivative. I'm going to go ahead and divide both sides by 6. Then, still don't take the derivative until you combine the y. So x would be equal to 2y. Only once you've gotten down to this easy configuration should you now actually go ahead and take the derivative. So taking the derivative of x would just be 1, and then, of course, dx dt equals 2 dy dt. And again, that's as far as we're going to go for the moment. So just like always, you should not be taking the derivative until you have rewritten or simplified your original equation into the most friendly format that you possibly can. Taking the derivative is still going to be the important step, but you want to do it at the time when it makes the most sense. So now let's go ahead and look at some more of the most popular types of equations that you are going to be asked to take the derivative of. And so not only is this kind of page here meant to expose you to the different formulas, it's also meant to remind you of how to take the derivative and then also be able to explain what it is you're finding. So something that I would perhaps write up at the top here, I mentioned it a couple of times throughout the lesson, but it really is important, especially in terms of what we're going to do here. When we've been taking the derivative, which we've done, for weeks and weeks now, we are used to thinking of it in terms of the slope of the tangent line. What you really want to now start thinking of it of is it's the ratio of change. So the fact that a derivative is a slope, and a slope, of course, is a ratio of change in y over change in x, or whatever the variables happen to be, that's really how we kind of want to start thinking about it. So these 6 examples, again, are 6 of the most common types of things we're going to be asked to solve word problems with. And we're going to start by being asked to implicitly differentiate with respect to time. So again, that means you're being asked to find d dt. And then most importantly, you're going to state what each rate actually represents. As we go to get into these word problems, you have no chance of actually solving for something if you don't know what it is you're looking for. So let's take a look here at number 1. This is the surface area of a sphere. So just like always, you're not going to have to memorize any equations. Hopefully some of these should look familiar, but we'll eventually make a nice list to help us. So the surface area of a sphere is A equals 4 pi r squared. we're now going to take the derivative with respect to time. So the derivative of a, remember that's really the same as taking the derivative of x. So the derivative of x would be 1, the derivative of a would be 1, and then you would have to follow it up with a dA dt. 4 pi r squared. 4 pi is a constant, so bring down the 2 times 4 pi would be 8 pi. R would go to the 1 less power, and then you would follow it up with a dr dt. That's as far as I want you to be able to do right now numerically, but now I want you to tell me what each of those values represents. So dA dt, this is the rate at which the surface area changes, and dr dt is the rate at which the radius changes. So again, not only do you have to be able to do the numerical calculation, but you also have to be able to explain it. After you find the surface area of a sphere, perhaps you'd want to find the volume of a sphere. So the volume of a sphere is V equals 4/3 pi r cubed, and we're going to do a very similar scenario here. So if V equals 4/3 pi r cubed, the derivative of V would just be 1 and then dV dt, and that would be equal to, so 4/3 pi, that's a constant, so treat it as such. So bring down the 3. 3 times 4/3 would be 4 pi. R would go to the 1 less power, which would be squared. And then you would follow it up with a dr dt. So explain what it is you're finding. So what is dV dt? It's the rate at which the volume changes. And then dr dt is the rate at which the radius changes. And yeah, maybe it's kind of a little bit repetitive writing it again and again and again, but the more you write it up front, the better your understanding is going to be as we get into some of the more challenging problems. So take a look here now at number 3. So number 3 is some form of the Pythagorean theorem where you would be solving for one of the variables. And then notice here, they are telling you that C is a constant. So that is very important. In these problems, there are going to be some cases where some of the variables are going to be constants. And when they are, it actually makes the problem easier, but you have to be aware of it. So again, the first thing I would maybe write myself a little reminder of is that this, again, is just a version of the Pythagorean theorem where they went ahead and set up x squared plus y squared equals c squared, but then they went ahead and solved for one of the variables. Before I go to take the derivative, just like always, I am going to do the rewrite step as c squared minus b squared to the 1/2 power. And now I'm going to go ahead and take the derivative. And again, C is a constant, so you have to make sure that you treat it as such. So starting on the left-hand side, taking the derivative of A, that would be dA dt. Then to take the derivative of the right, you're going to bring down the 1/2. You're going to take the entire quantity, c squared minus b squared, to the 1 less power, which would be negative 1/2. And then you're going to have to go ahead and use the chain rule. That's still a thing, which means you're going to take the derivative of the inside. When you go to take the derivative of the inside, please make sure you remember that C is a constant. So as you go to take the derivative of a constant, that would just be 0, which means you only have to take the derivative of negative b squared. And so you're going to go ahead and take the derivative by bringing down the 2, negative 2 times b. Then, because of that chain rule and because you did the derivative in terms of b, you're going to have to go ahead and follow it up with a dB dt. So then I would go ahead and just make it a little bit cleaner. So let me set a little bit more room. I'll go over here. So dA dt would be equal to 1/2 times negative 2. That would be a negative b. Bring down the square root of c squared minus b squared, and then don't forget dB dt. So dA dt equals negative b over the square root, or to the 1/2 power, remember, doesn't matter, times dB dt. And then don't forget to explain what it is you found. So dA dt and dB dt are the rates at which A and B are changing. I'll just kind of write it once as opposed to writing it for each one. So treat constants as such, the derivative of which is 0. Even if you're doing the chain rule, first of all, don't forget the chain rule. And second of all, if you do, don't forget to follow it up with a d whatever in terms of t. Then let's go ahead and take a look at number 4. So this is now the volume of a cylinder. So the volume of a cylinder, try to envision it. It's a bunch of different circles stacked up on top of each other, which is why it's the formula for a circle, pi r squared times the height. Notice again that r is a constant, so you are going to treat it as such. So taking the derivative of v, that would be dv dt. And again, r is a constant. So that means pi r squared, that is a constant times h to the first. So basically, if you're taking the derivative, you would bring down the 1 times the constant, which would be pi r squared. H would go to the 1 less power, which would be 0, so it would go away. But because you were doing the variable of something with the height, you would have to follow it up with a dH dt. So dV dt, that's the rate at which the volume changes, where dH dt is the rate at which the height changes. So take a minute to kind of catch up, digest a little bit. I'm sure your teacher is pausing this often for questions. So if you do have questions, now would be a great chance to ask. You're going to see a ton of related rate problems over the next couple of weeks. And again, this is all just really meant to kind of get your feet wet. So number 5, a little bit fun here, we have the cosine function. So the cosine of theta is equal to x over 15. And just to kind of remind you why that's allowed. So take a look and make sure you note that this is a right triangle. When you have a right triangle, you can, of course, use SOHCAHTOA. A cosine would be an adjacent over a hypotenuse, which is why the cosine of theta is equal to x over 15. Sometimes we'll use sine, sometimes we'll use tangent. So all of those are available to you. As we go to take the derivative, so you actually are in the best format, except on the right, instead of x over 15, you want to rewrite it as 1/15 x. If you remember that those are equivalent, it's just much easier to take the derivative in this form. So the derivative of the cosine of something is the negative sine of the same something. And because the something in this case is a theta, you have to follow it up with a d theta dt. The derivative of 1/15 x, so the derivative of 1/15 x is just 1/15. And then, of course, follow it up with a dx dt. What's going on here? So d theta dt is the rate at which theta is changing. And of course, that means that there would be an angle. And then dx dt is the rate x is changing at. And then finally, last but not least, we have the volume of a cone. So the volume of a cone, take a look, V equals 1/3 pi r squared h. Now compare this to number 4, where they told you that r was a constant. I mean, think about a cylinder. It's the same radius all the way from the bottom to the top. Think about a cone, that is not the case. You have a smaller radius, if you're thinking about an ice cream cone, you have a smaller radius at the bottom of the cone as compared to the top of the cone where the ice cream is. So that radius is not changing. Because of the fact that that is the case, we actually have 2 variables here. We have r variable and we have h variable. So that actually means that we are going to have to use the product rule. As we use the product rule, don't forget to take all of your derivatives in terms of t. And in terms of the first, so I'm going to make 1/3 pi r squared my first, and then I'm going to have h be my second. So last problem, and kind of as hard as it gets for today, starting with the derivative of v. So the derivative of v would be dv dt. So then the first would be 1/3 pi r squared times the derivative of h. The derivative of h would just be 1, but of course, follow it up with dh dt, plus the second, which is h, times the derivative of the first. So the derivative of 1/3 pi r squared, 1/3 pi is a constant. So bring down the 2, that would give you 2/3 pi. R would go to the 1 less power, which would be r. And then because you're taking the derivative in terms of r, that's why you would have dr dt. So really kind of a good way to end the lesson on, because not only do you have to take all your derivatives in terms of t, but you also have to use your product rule. This is probably the most variables that you might have in one problem. And again, just to reiterate, dv dt is the rate at which the volume changes, where dh dt is the rate at which the height changes. And of course, dr dt would be the rate at which the radius changes. So honestly, I think you're going to love related rates. We're going to do a couple of days of it. Each one is going to kind of focus on a different shape and a different type. But I really think you're going to like them once you get into a nice, routine of them. I actually think that they're kind of fun and interesting, and certainly the most direct real world application that we've had. So there is no homework that goes along with this specific lesson. This is all just to set the scene for when you actually get into the first day tomorrow. So thanks very much, guys, for tuning in, and we will catch you next time.